Hello everybody, this is Colin here. Thank you for joining us. So the purpose of this webinar is for us to just take a look at the criteria and data needed. And I've picked two examples of sort of the second or analytic level for use of real asset information in the GIS context. And that is two things. One, repair prioritization, and the other one is modeling replacement costs, specifically in water and sewer networks. So those are two examples we'll use within the context of, well, what criteria, what data is needed to be successful in doing some of these activities. I've been involved in countless projects in a number of geographies, and it's really kind of interesting as to where the focus is. And so hopefully this will be useful. So I'm Colin Hobson, CEO for Open Spatial, for those who have not met me. But let's get started. And to get started, the first thing is, well, what is your organization's mission? And from that perspective, what we mean is these are the questions that we're trying to answer. And so there are multiple levels within the organization, going from planning to levels of service. And so those are sort of one matrix if you're in management in an organization or you're even consulting to an organization. These are things to bear in mind. These are the problems or the context within which we're solving various problems. If you're an open spatial, you're probably also involved in, well, what technologies can support those. That's a whole different webinar, and we can get to that. But from our perspective, we've really helped a lot of organizations not only gather their data, but do stuff with that data. And the context here is what stuff, and well, what data do you need to do what? Once again, water and sewer network. In the middle of this diagram are a whole lot of functions that happen within an organization. And these are by no means exhaustive. There are a lot of others. But if you look around this, essentially, what do we have in terms of assets and where are they? And from there, you can build it out based on planned as constructed or as built documents. You can look at aspects like if you have a new customer or a customer changes or you add new stuff into your network context. Or if there's a new survey or you've got a leak, all of these are going to require data. And once you have this sort of data, you may go to a higher level and say, well, what about one of the topics in this webinar, and that's replacement projecting and planning. How do you project what you're going to replace? And we'll take a look at a couple of examples on that, and how do you plan for it? Other things, normal operations reporting, dial before you dig, capacity modeling, connectivity, service-related stuff. All of these are factors that an organization as a whole kind of deals with. And so from the asset management / GIS perspective, what data do you need and what are the key criteria within that? And so if we look, typically or often we'll get to places where they have a limited asset inventory. So in the initial phases or first number of years within an organization, they're really about this, and that's building the asset inventory, getting it mapped, both the mapped and the non-mapped things, and just building out data structures and coming up with different ways to confirm and build out. But once you have a fairly good data set, you can do stuff. The other thing is, if you don't have a decent data set, what things are most important to collect? And that's sort of another theme that you can gather from this particular webinar. Once again, probably another presentation to run through all of those things, but this is sort of the life cycle here where you get an asset inventory, a whole lot of steps. You look at things on the asset management side, like when was it installed, what did you pay for it, and obviously there's a whole lot of financials go with that. Assessing condition, and then kind of building and assigning cost and expected life, and looking at maintenance activities, so operational stuff, planning and management things can build on top of a key data set. For this presentation, I'm really looking at two different things. Repair prioritization is one set of essentially analytics, and then modeling replacement costs is another one. So those are the two examples I'm using just as a context of, well, what are the data that's key and the criteria that you use for that. It all boils down to the whole point of doing this is so that we can get a long-term sustainability, not only operationally, but in long-term replacement and budgeting. So the things we're trying to answer is, how do you identify what you're going to need to replace and when? How do you prioritize those? And, if you've got limited budget, well, which things do you prioritize over other things? And then what will the exact costs be? And if you do it now, etc., how can you sustain a particular level of service? So as I said, we'll look at water and sewer networks, and we're looking at these two aspects, repair prioritization and replacement costs. And then toward the end, last couple of slides, we'll look at key criteria and data needed within that. So what data? What do we mean when we say real asset information? And so this can be a whole mix of things. I kind of always say, well, what do you actually have? And it can be, you've got a lot of plans, or you've got actual drawing files, or you've got specific as constructed documents, and they can be anything from pretty analog like this to where you build it out and you've got an asset inventory. So that was actually a real example of taking that customer through those paper documents to get to essentially a water network. And part of that was prioritizing, well, what do we capture? How do we capture it? So that they can then come in and look at this, and now they actually have a map of real asset information where everything is now structured into the kind of assets, the types, and it's all connected, and we've got the attributes of that. And so that was water and sewer. So this is a real, example where we've built that out for them over time. A lot of folks already have a pretty good inventory of stuff, and so you can go in and you can know all the diameters and materials and locations in relation to each other, etc. And so you go. And it becomes really good for operational purposes. So you can say, here's the valve for, there's the connection point for that hydrant over there, that sort of thing. And if you're in Munsis, you can work your way through building that with, this would be one of our tools for building out, in this case, a sewer network that's fully directional, connected, topological, and attributed with. So that 8-inch is actually parameters off of the line. And so you've got all of this kind of tools for ensuring good data capture. So stepping back then, just showing you essentially from paper maps and drawings, what we're doing is building out real asset information or asset data. And that includes then whether they're connected, but also all of the attributes. Once you have that, you can start the modeling perspectives and build it out. And so this little overview is sort of starting from the beginning, building out those data sets. Sometimes this can be years and can be various levels of completion, but this is actually a model. In fact, I'll be running through the same concept used in this one, where it was a repair prioritization for a sewer network, and it had to bear in mind drainage, particularly within wetland, and these would be schools and hospitals, and then obviously just the age, so proximity and various other things. So I'm getting ahead of myself. So this asset intelligence is important for building out really the way in which you can use that information and start building that life cycle where the data you're collecting is not just operational, it also becomes part of the ongoing planning for that. So let's look specifically at repair prioritization. Finally, actually, that last picture that I showed you, that was built out by going to look at the actual factors of the condition, probability of failure, and consequence of failure. And so a condition score was built out, and then the probability here, and I'll look at this, but essentially a factor is built out for each of these where you've looked at age and you've put a factor. Typically, I prefer to have a big number if it's bad and a low number if it's good. So if you do them, from 0 to 10, then 10 would be bad, or 0 through 5, depending. And then you go in and look at probability. Here is the age, and the material will give you some sort of probability. So this would be applicable, particularly in sewer and water. We're taking pipe diameter as a measure of the consequence. In other words, a super large pipe would have much more consequence if that broke than a smaller pipe. There's various other factors here, and we'll look at those things like environmental proximity, just construction, how difficult is it to get somewhere, and critical crossings. If you're in a major urban area and there's a lot of other infrastructure going on, then that's a problem. There's a technique you can use if you have this sort of thing where you've got a set of two factors here that turn into a number and factors here that turn into a number, and then you want to take these two scores and put them there. You can go, if it's high probability and low consequence, then it gets essentially a lower number in this matrix compared to the high number to be there, the lowest number would be here. If there's a low probability but a high consequence, that would get a higher number than something down here, for example. So it's just a way of matrixing in different things. So what you can do there is build out the score. And when you get to a total score, that score can get weighted so that you can put them, A, B, or C. In this case, a category C means you really need to replace this within 5 years. And that's in relation to everything else. So it's all kind of relative. How bad, according to all these factors, this one's going to be a higher priority than the other. And it does account into it age. There's lots of different techniques for modeling. So here would be, you split. This is the actual age distribution for this organization for their, in this case, sewer pipes. And they've been put into 5-year periods so that we could split it, and then going into looking at that, you can look at what's the count and what's the lengths, etc., because you've got real data. In terms of those other ones, the age, this lot uses 0 through 5. assign a value. So if it's 0, then you're not going to end up getting any values. A high value, it's kind of important to be consistent what's low and what's high, and look at the maximum scoring. So sometimes when you're doing a model like this, and I'm not going to go into the intricacies of setting up those models, but you do have to balance out different things so that one factor doesn't become overpowering over another. Or in fact, if you want like diameter and age, they are fairly important, so you may want to have them as a higher number than these others. So these ones can only go 1 through 3, for example. But things like construction, easements and traffic, so access, those are factors that were taken account of, and overhead utilities. This particular city had a bunch of overpasses for traffic areas, and it was difficult to get down below, and if you went below, you limited what you could and couldn't do. Also in hospitals and creeks, given a higher priority because the area was low-lying next to sensitive water and large population. So in essence, accounting for the fact that you might have sewer spillage going and being dangerous. So anyway, moving along, here's an insight into it. So you could run a couple of different scenarios. There's sort of the orange one and the green one, A and B. This is sort of calibrating the model and seeing as you change the limits. So if you looked at age, if you cut off at 50, what's the impact? Whereas on this one, if you cut off at 100, what's the impact? And it sort of changes things a little. You can then go in and do the math. You can do it in database. You can do it even in a spreadsheet. This was started out as a spreadsheet like this. But the fact is, you have chosen, and that's really all that I'm going to focus on here, apart from the internals, but you've chosen specific criteria. And you need to have that collected. So you really do need the install year for every bit of asset. So that becomes something you really got to capture. And I focus on that because a lot of people do not build that into their data capture. They just want to know where is it and what's the diameter and material and type and that sort of thing, using a pipe as an example. But in this modeling, you're going to come out with a category A, B, or C, and it's really built out on a relative score. And because it's actual GIS data, we can come back to a map and show where category C is the stuff that's old. This is probably why they were doing the model, because you can see they've got old stuff kind of everywhere. And that makes it difficult to prioritize which you're going to fix first. And I'll talk about that just in a minute. You can choose a zone like here and say we're going to fix that as one project. And then the year after, we're going to go and work somewhere else. In the meantime, you're going to do amelioration and or mitigation in some of these other areas just to be aware that they might fail. And so that's interesting. And the other thing is, as you replace stuff, you got to obviously go and fix it. So that was that model, and it just builds it out. So that's repair prioritization. Here's another one. If you're doing specifically in water, this is a different customer, but they were looking at just modeling out water breaks. So we're still looking at repair prioritization at this point. We actually took their Munsis data set and threw it to the Oracle Analytics Cloud and did two things. One is go tell the computer, AI, tell me what you can find. And the other one is apply our logic and say, well, we know there's a certain set of things that are probably likely and we're going to run through those. Interestingly enough, it kind of the one helped the other and the other helped the first one too. Here's a list of water breaks. You can actually, here's the entire list. They're broken up into different types of breaks. There's quite a lot of leak general, so really basically bad data, which is always a problem in this. But there's still good data here. They've got about 80 years of water breaks, a number 100 occurrences, heat map there. And then looking at this, you can actually go in and see that data. It's a live thing. As you zoom in on out the map, it'll slice and dice, which is kind of nice. You can look at the breakdown of breaks and the causes over time, and you can go in and say, okay, we'll model out what's the predictive breaks. And if we looked at that, what we've done here is this was done in 2018 and we modeled out 5 years and then we ended up modeling it out 50 years. But the thing that we picked up is you can go in and look at, in this case, there was some environmental factors, official deposits, a particular soil type there, and asbestos cement pipes, which is about 50% of their pipes actually. And looking at them, how does that relate to the breaks? And with a 95% confidence in the trend, we can look at the break. It's going up with ACP pipes. But that knowledge within the system actually hid two things. So we came back and picked up that these three pipes, ACP, PVC, and CIP, they've got the predominance of breaks. And this trend, it doesn't look so bad for the water breaks. And we modeled, as I said, modeled that out all the way to 2050 and predicted it out. But that trend line of all the breaks together hid the hidden factor, and that is that ACP here on this bottom chart, by the year about 2035, 80% of their asbestos cement pipes are predicted to have some sort of leak. as opposed to the others, the VCP and the CIPs. Those ones were pretty fine. So this chart up here hit that. And so anyway, once again, I'm not going into all the details of the modeling, except of, well, what data do you need to be able to run a model like this? That's sort of the factor. And what's important, this here is a multi-million-dollar bit of knowledge right there as to, well, that's the focus, and those guys are failing, and you gotta go look at them. If you're looking at replacement costs, I'm going to switch gears just a little to the financial, but it's based on the same. In the US, this example is the EPA, Environmental Protection Agency, which essentially manifests itself down to water quality control boards across many, many states and various names like that. But their job, in essence, is to run governance and authority and organizational checks and balances, and funding, of course, but checks and balances on operation and delivery of particularly water in this case. So I've just running through an example of a project using the EPA tools for basically simple tools for effective performance, the STEP procedure. That's a guide series that they put out, and pretty much going around to all the water authorities and make sure that this gets applied in terms of budgeting. Now, this is the small version for smaller water authorities, but pretty much the goal for this is to ensure that the water authority has enough money in reserve to replace the current infrastructure as it ages out. So in today's dollars, ensure that as things get old, you have enough money to actually replace them, just to sustain. This is not even about growth or that. This is just to replace, just accounting principles. Okay, so they've got a few steps: identify. So this is data capture, look at condition and service history, get the useful life, get ages, and then go in and actually start tabulating this lot. So you'll be looking at this sort of information, estimated useful life, all the way down to, different pipe types, but this is point features and line features. And so you've got to kind of figure that out, because if you know that, then it's a predictable problem, right? This is an example where we did this analysis with them and spent a fair amount of time getting age assigned to every single pipe section. And there's different ways of doing that. From that, if you've got a full set of water pipes in your GIS, what that means is you've still got to go in there and categorize and group that such that it's a manageable thing. Because if you've got a number of thousands records of each little pipe segment, we've got to actually start grouping those. So the step process, we did put it into a bit of a user interface here. So you can go and look at the map. That's where we were on this previous slides. But taking all of these instances of every little pipe section and every little point feature and pump stations and the pumps and all of that sort of stuff, you can go into something like this and split it into linear assets, point assets, and other assets. So the linear assets, we just looked at, well, you've got to go and assign a priorities. So here's, we were mapping them, looking at age on everything, categorizing that. So when you get age here, that's a whole lot of numbers. So you kind of group those. We went in decades in this instance and grouped them so that pipes are grouped on 4 characteristics: the material type, the diameter, the decade, and the condition. So those 4 together make one particular permutation for that row, right? So this is all pipes in 1960s, 6-inch asbestos cement, good condition. Those all group together and they have this particular length, and the expected life of a pipe of that type of installed at that age would be 105 years. And so we know now that its age is 60, remaining life going to be 45. So this is following essentially the step process. This is just a user interface. You can override it, and this is just a word about condition. Condition's actually pretty tough. It's fairly easy to collect. It's a lot of work to collect it. Certainly pipes are not as easy because you can't, you've got to literally walk down it or do any number of measurements from external or internal. The problem in modeling that stuff is you just will pretty much never have condition, an up-to-date condition measurement of every single pipe section. And so it's hard to apply that knowledge. One of the working criteria is for where you do have a condition value, particularly the ones where it's in bad condition, you really do need to account for that because you know that. The fact that you don't know which other ones may also be in bad condition is sort of an unknown. And, people have to use experience and go and search, and also you can prioritize by going to look at the older ones until you see a trend and you kind of work on it. So condition is one of those sort of difficult ones. The install date is fairly easy, diameter is easy, material is easy. Those are attainable, should have it in on the record, and if you don't, you can go and collect those and build them in. Conditions a little tough. Expected life is essentially a record keeping and investigation on what do you have, where it goes. But this grouping is fairly interesting because this is your primary asset information. So there's different things done for these, but to understand now, instead of having thousands of different kinds of pipes, with these 4 criteria, this, in their instance, boiled down to 72 different rows in this table. That becomes quite manageable. Now we can do something with that. And those particular ones, I'll go to the next one, and that is years till action. If you prioritize, you can see the 1950s 12-inch cast iron pipe. Even if it's in good condition, we really think it's going to need to get replaced within the next 5 years. So this listing is where you're actually now coming in and looking at what you're going to need in terms of money, but you've actually gone through a prioritization, and the prioritization accounts for things like this is a large pipe and it is the only connection we have to the supply, so it becomes more critical, so you prioritize it. If you're looking at point assets, if there's no backup pump and that pump is running a relatively large set of customers within your organization, and maybe there's a hospital there, then yeah, that becomes a higher priority. So you've accounted for that. Point being, you've got a list, and you can, the interesting part is you can show them on the map. You can just toggle it, turn it on, but it'll do those group and you'll see where they are. Moving on for the reserve, this gives you an idea of what the money is involved in replacing it. And so it's useful to look through, you know, you've got like 6 million for these sets of 6-inch pipes, and there's about 13 years left. So that's going to have an impact. And depending obviously on the size of your organization, this would change. But from there, you can then come in on your organization and do a simple chart like this. So this is really useful. So accounting for priority, accounting for redundancy, and looking at whatever we have condition. That being said, for all of those years together, we know what the useful life is, age, remaining life, and hence we can literally go in for each, in this year, a 5-year period from today, how much money in today's dollars to replace it, and when does it need to be replaced? And that's essentially that step one. So these ones you can see, huge panic 15 years from now. Well, now it's actually 13 years from now. This was done a few years back. Looking at that, before you present it to the board, you might want to go and look at your numbers. You might start putting together a plan to say, you know what, we got to start right now. We actually have to raise the rates a little, but then we're going to guarantee they're going to be better later on, because this is the good news trend all the way down. And so that is very useful information. So those are 2 examples of one being repair prioritization, this one being modeling out replacement cost. And I've just used a particular test. So let's go in then and kind of summarize that. So in those 2 examples, the things I've mentioned, location, and then it's what I call primary asset information, the type, the size, date installed. Condition, there's things like criticality and then dependency, particularly linear networks, dependency on what it's connected to, how it connects, where the supply comes. There's a few factors in there. Cost to replace may become important, and expected and remaining life. And so with these 2 different examples, I've kind of put this chart together in a few comments. So if you step back, the ones in the darker color are probably more in what I've presented in those 2 examples specifically, and the lighter color need to be tracked, but are not as critical for satisfying that modeling what we've tried to apply. So what that means from a GIS perspective is condition is going to come from your field crews, from your asset management system, usually your work orders. You're going to track that, but it's very hard to apply to a model because, as I mentioned, you're going to have a whole lot of assets that nobody's actually measured the condition. Age is a predictive. Expected life is not a perfect scenario, okay? And that can be impacted by some of these other factors. And so once again, they become sort of like condition. You don't have it for everywhere, but it may be important. So if you are doing like for repair prioritization, one that comes up fairly often and actually is important is on the environmental front, things like roots and trees and vegetation. Those would be a factor that you might want to build in here. So I haven't put it in. That particular example I showed was more of a city and environmental there that they had done fairly well managed tree control, and that had essentially a good program, but it still had an impact. And so that if you look through, you know, a number of papers published on repair prioritization, particularly with sewer, things like roots and trees can be critical. So if we look then at repair prioritization, the actual type of asset is important. Some assets last a long time, others don't have an expected life. You've got to know the type, or you can't come back and start trying to look at anything about that. The criticality is sort of dependent on where you are and what's important. And so these are actual factors. On the replacement cost, it's really the cost of figuring that out. What's the useful life and what's the cost to replace? That's important. And so these others like criticality and dependency need to be accounted for, but without actually even putting that in, you can still come up with a model that's got an answer, got a predictive anyway. How accurate it is depends on all of these factors. One of the other things of the expected remaining life that's a challenge actually in both of these is that turning point of cost to replace versus cost to repair. Now, it's usually more complicated than that, because if you repair one thing, you kind of want to be doing the job for a bunch of things around it, or if you repair one thing that's dependent on others, you don't want to replace the pump and not look at what's going on with the pipes, that sort of stuff. There's more to it than that. So these models really not going to tell you absolutely everything, but they're definitely going to give good guidelines. And the sorts of data you need is fairly basic. So from a GIS perspective, this comment before I leave this slide, determine the level of accuracy. So location. For these two things, repair prioritization and replacement cost, it doesn't matter if your data is only within a couple of meters of where it's located. For other purposes, yes, you might want it to be, close to centimeter accuracy, but it's more important to have everything surveyed, or no, I shouldn't use the word surveyed because that implies accuracy, which is great, but I mean, you should have everything accounted for. Because if you're missing large tracts of pipes or development, city bits, you're going to come out with an incomplete model. So it's more important then to actually have what assets you have, type, size, and age, than a very, very accurate location. So as you're planning out your GIS, you've got to think of, well, what is it we're trying to satisfy? It depends. It's winter in the Northern Hemisphere, and one other thing going on right now is if there's a water break, they've got to find a valve under the snow. And if you don't have an accurate location, then that becomes fairly critical. But it's critical for operational purposes. And so for these two models, we've missed that out. So, just to bear in mind, there are other factors on that. But location is important, but at least knowing whether you have something there or not is even more critical. And so that's really what counts. So that's sort of the data needed. On the criteria side, you really do need a documented asset inventory. That's just where I was going with those last statements. And for that purpose, you want to know the primary information. So we spend a bit of time going through those, and I've put them in a different color because that's the actual, essentially data that you need to be able to do these kinds of analytics, condition, criticality, replacement costs. There are also other aspects, of course, within an organization that you would want to figure out, and that is what are the other plans? If you're busy over here and there's a whole new development going in a different area, often those updates to infrastructure are tied in with, say, new development or a rezoning or a whole improvement plan. And so you've got to look at that. There's also budgeting, depending on the financial health of an organization, tying that back to rates and that sort of thing. How are you going to get that money? How are you going to build it out? And then prioritization as well in terms of level of service or performance, etc. So point being, you're going to have intentional actions, and that is going to build out to an operational and financially resilient organization that can provide essentially sustainable levels of service. And so it's a multidimensional problem, and certainly the information that you're building out is critical. It's important, and one can do it in a planned fashion. So I just wanted to kind of get that overview and look at the criteria and the data needed for the successful building out of these kinds of analytics for ongoing planning and obviously immediate operations and maintenance. Thank you very much. If you have any questions, this is my contact info, but any of the open spatial offices would be useful. Thank you very much, everybody. And we do have a webinar. Our next one is in February, and it's looking at QGIS, how to use that with the Mensis data. And there's a lot of new things in there, a lot of depth of functionality and analytics. So thank you very much.